All right, let's talk about Go. If there's one single feature that really defines the language, it's got to be the way it handles doing a bunch of things at once. Its concurrency model. And what's amazing is that it all boils down to just two core ideas: Go routines and channels.
Now, this is basically the entire philosophy of Go concurrency in one sentence. It might sound a little bit like a riddle at first, right? But it's a huge shift from how things were usually done, which often meant using complicated locks and mutexes to stop programs from tripping over themselves.
So let's actually break this down. We're going to see what this really means in your code. And we'll start with the actual workers in Go's concurrency world, the Go routines.
First up, Go routines. Think of these as the incredibly lightweight workers of your program. A Go routine is just a function that can run on its own at the same time as the rest of your code.
Here's the best way to think about it. A traditional operating system thread is like hiring a whole new full-time chef for your kitchen. It's a big deal, it's expensive, it takes time to get them started, and it has a lot of overhead. A Go routine, though, that's like snapping your fingers and getting a magical kitchen helper instantly. They are incredibly cheap, start up super fast, and start with a stack of just about 2 kilobytes. Compare that to the megabyte or more for a regular thread. This is exactly why you can have thousands, even millions of them running at once.
And you won't believe how easy it is to start one of these magical helpers. You literally just put the word go in front of a function call. That's it. Your main program doesn't wait around, it just kicks off that new task and moves on. So now we have all these little workers running around. But how do they talk to each other without causing complete chaos?
Well, that brings us to the second pillar of Go concurrency: channels. If Go routines are the workers, channels are the safe, organized communication pipes that connect them all. So what is a channel? It's basically a typed pipe that you can send values into and receive values from. The best analogy is a conveyor belt. One Go routine puts something on the belt, and another one, somewhere down the line, picks it up. This whole process guarantees that things are delivered safely and in the right order. It's the main way Go just elegantly sidesteps classic bugs like race conditions.
And here's where it gets really cool. Channels aren't just for communication, they're also for synchronization. Your main function can fire off a bunch of Go routines to do some heavy lifting, and then it can just wait. It waits to receive the results from a channel. It doesn't have to pull or check statuses, it just blocks until the work is done and the results are delivered. It is such a simple and beautiful way to coordinate work. Now, this is where we need to dig a little deeper, because not all channels are created equal. The difference between an unbuffered and a buffered channel is absolutely critical. It completely changes how our workers coordinate with each other. Think of an unbuffered channel like a baton handoff in a relay race. The sender has to wait for the receiver to be right there at the exact same time to make the exchange. It's a direct, synchronous handoff. A buffered channel, however, is more like a mailbox. You can drop off a few letters without waiting for the person to be home. The sender only has to wait if the mailbox is completely full. This is a really powerful way to decouple parts of your system. So let's break that down. An unbuffered channel has a capacity of 0. It can't hold anything, so a send will always block until the receiver is ready to take the value. A buffered channel has a capacity of 1 or more. A send only blocks when that buffer is full, and a receive only blocks when the buffer is empty. This small difference has massive implications for how you design your programs. So this brings up a really important question, doesn't it? If an unbuffered channel needs that perfect rendezvous, what happens if one worker shows up for the handoff, but the other one never does? The answer? You get a deadlock. The Go routine that's trying to send is just stuck, waiting forever, and your whole program grinds to a halt. But one of the fantastic things about Go is that its runtime is smart. It can often detect these simple deadlock situations and will just panic with a really clear error message, which can save you hours of debugging headaches. Okay, so to avoid those deadlocks and other weird issues, we need to follow a few simple but crucial rules for using channels. This is especially true when it comes to signaling that a conversation is over. All right, let's walk through the rules of closing a channel. Rule number 1, and this is the most important one, only the sender should ever close a channel. Why? Because only the sender knows for sure that no more data is coming. Now, if you try to send data to a channel that's already been closed, your program will panic. But, and this is the key, you can always receive from a closed channel without blocking. This is how you signal that the stream of data is finished. So why would you even close a channel? Well, the most common reason by far is to terminate a for-range loop that's reading from it. A for-range loop will just keep trying to pull values from a channel forever. Closing the channel is the signal that tells the loop, hey, we're all done here, you can stop now. If you forget to close it, that loop will just block forever, waiting for more data, and boom, another deadlock. Now, to handle this done signal a bit more explicitly, Go gives us this really neat idiomatic two-value assignment when we receive from a channel. The second value is a Boolean, usually called OK. OK will be true if you got a real value, but it'll be
so we've
false
covered
if
the
the channel has
fundamentals.
been closed
You ready to get
and
into
all
a
the
more
values have been
advanced
read.
but super
It's a
powerful
crystal clear
tool
way
that
of
senior
knowing it's
Go
time to move
engineers
on.
use for really fine-grained control? Let's talk about the nil channel.
A nil channel is exactly what it sounds like. It's a channel variable that you haven't initialized with make. Its value is just nil, and its behavior is dead simple and absolute. Any attempt to send or receive on a nil channel will block forever. It's like a conveyor belt that's been permanently switched off and unplugged. The behavior really just boils down to 3 simple rules. Sending to a nil channel blocks forever. Receiving from a nil channel blocks forever. And trying to close one, that'll cause a panic. Now, blocking forever, that sounds pretty useless, maybe even like a bug, but it's actually an incredibly powerful feature. So why is this a feature? Because it lets you dynamically turn parts of your code on and off. Inside a select statement, which is waiting on several different channel operations at once, any case that involves a nil channel will simply be ignored. So by setting a channel variable to nil, you can effectively disable one of the options. Then later on, you can assign a real channel back to that variable to turn it back on. It's a really elegant trick for managing complex state. We've covered a ton of ground here, from the lightweight Go routine to the synchronizing power of channels, and even the expert-level trick of using nil channels to control program flow. The real magic of Go concurrency isn't in any single one of these pieces, but in how beautifully they all combine. So the question to leave you with is, what awesome, robust systems are you going to build with them?